All right, in this video, we are going to start our discussion of functions. Now, what is a function? Well, a function is actually a relation, right? And so here's what our definition is going to be. A relation F. So a relation F. A relation F is a function. We're going to try to be color coordinated today. A relation F is a function provided we know about relations provided the ordered pair A, B, and F and AC in F implies that B is equal to C. Now, what does this actually mean? Let's try to make some sense of this definition, right? Let's think of now F, it's a relation, right? So it's going to be a set. Its elements are these ordered pairs, right? And let's think of the first element in the ordered pair as an input, right? And then the second element in the ordered pair as an output, right? And we're familiar with functions, right? Like f of x equals x squared, right? We have inputs and outputs, right? And so what this definition is telling us is that every input has a unique output, right? So that's why I said that if AB is an F and AC is an F, then B must be equal to C, because each input, A, must have a unique output. So that's what this definition is saying. But now let's write our function in some better notation, right? Let's do this in some notation that you're probably familiar with. So function notation. And just as a heads up, this video is just going to be pretty much a ton, well, not a ton, but everything that we're going to do is going to be definitions pretty much. Yeah, just wanted to throw that out there. So function notation, right? We're going to say, let f be a function. Let f be a function, and let A be an object. A be an object. There we go. Now we're going to say the notation, here it comes, the notation f of A, so that's how you read that, you say f of A, is defined provided there exists an object B such that AB is an element of our function f, right? And if that's the case, so in this case, what we say is f of A is equal to B, right? And this is something you're familiar with here. Let's do an example, right? If we have a function defined, say f of x is equal to x squared, right? Then we know that, let's say f of 2 is equal to 4, right? 2 squared is 4, so we would say that the ordered pair 2, 4, sorry, I have no idea why I said 2, 4 is in F. So it happens when you start thinking faster than you could speak. All right, so there we go, right? That's basically what we would say. And if we wanted to write functions in set builder notation, right? Let's say with our example with x squared, what we could say is we could say f is equal to the set of all ordered pairs, let's say x, y, such that, and we're going to do this over the integers because I don't want to do this over the real numbers. So we're going to say that f is equal to the set of ordered pairs x, y, such that x comma y, they're both in the set of integers, right? And we're going to say y is equal to x squared. So that defines our function, and that puts all of our ordered pairs into one set. Now, the next thing I'm going to talk about are the domain and the image of a function. Domain and image. Sometimes you might hear the word range. That's usually a word people tend to be familiar with, at least in my experience. Image, range, they're used interchangeably. It just, whatever your textbook is telling you to use. I'll be using image, right? So domain and image, what is that? Let's scroll up a bit to give ourselves some space. So, we are going to let f be a function, as we do around here. Now what we're going to say is the domain, here let's use our blue, let's try to stay color coordinated. The domain, there we go. The domain is going to be the set of all possible first elements in the order of the ordered pairs in F. Of ordered pairs in F. Ordered pairs in F. So that is our domain. And then we're going to say this is denoted. This is some weird notation. I never really see it, but it's going to be denoted the dom F or dome F, however you want to pronounce that. DOM-F. There we go. Now, our image definition is pretty much analogous. So what I'm going to say is the image is the set of all possible second elements in the ordered pairs of F. In the ordered pairs of F. There we go. And this, can you guess what it is denoted by? I don't like this notation, actually. It's denoted MF. I don't like that because M could also be imaginary, but, we'd be using the same notation for multiple things in math, so who am I to complain anyway? But yeah, there you go. You got your domain. The domain is the set of all possible first elements in the ordered pairs. In F, denoted dome of F, and then the image is the set of all possible second elements in the ordered pairs of F, denoted the MF. There you go. So let's think about what domain and range are in specific examples, right? So let's say if we have, here, let's use blue again. Let's say f of x is equal to x squared. And we're going to do this over the integers, right? So let's say over the integers. Just write that out in English. Over the integers. Then the domain of f in this case is going to be the integers, right? Everything that is going to be the first element in our ordered pairs will be an integer, right? And then the image of f is going to be the set. So the image, the second element, is going to be the set of all perfect squares. That makes sense, right? Like 25 is a perfect square. It's going to be in the image of f because let's say you put 5 as your first element, 5, that squared is going to give you 25. Hopefully that makes sense. These are familiar concepts. We're not doing anything crazy yet. Now what I'm going to show you is some notation that you may have not seen before. Let's look at our new notation. I'm going to write it right here. Oops, sorry about that. We're going to have f like that. You're probably thinking like, Johnny, what is that? How do I even say that? I've never seen that before. What we're going to say let f be a function and let a and b be sets. And let a and b be sets. There we go. Now what? What we say is f is a function from a to b, right? So here's what we're going to say. I'm going to say f, here, we say, and I'll write this in blue, I guess. We say f is a function. F is a function from a to b, provided the domain of f is equal to a, and the image of f is equal to, not equal to, is a subset of b, right? And there's also, like I said, f is a function from a to b. You might hear people say f is a mapping from a to b, or yeah, function from A to B, mapping, they're interchangeable. You'll hear people say it in both ways. The key thing in this definition is that the domain of f must be equal to A, which is, again, some set, and the image of f must be a subset of B, which is some set. Those are some key differences right there, right? So let's think about our f of x is equal to x squared example, right? We say, let's say, like, let f of x equal x squared, right? That's our function, right? Then the domain of A, right? We could say f is a function from the integers to the natural numbers. Why is that? Well, remember, the domain of f, as we said, is going to be equal to the integers, right? Because we were, and this is over the integers. Here, let's write that in parentheses, over z. Because you could do it, you could change up your domain. We're doing it over the integers. So the domain of f is equal to z. So there we go. A is equal to our domain. And now the image, though, right here, b is equal to the natural numbers. Our image in this case is not actually equal to the natural numbers. Our image of f, remember, is the set of all perfect squares. And it just so happens that the set of all perfect squares is a subset of the natural numbers. So this is a perfect example to demonstrate where our domain of f must be equal to A, which again is z, and our image of f is a subset of B, which is our natural numbers. So I just want to emphasize that. Now what we're going to do to end this video is talk about counting functions, right? And what we're going to do is we're going to talk about counting functions that go from some set A to some set B. Because when we think about it, right, there's not just one function from the integers to the natural numbers. And since those sets are infinite, there are infinitely many functions I can define over those sets. But I want to talk about our finite sets. So we're going to say let A and B be finite sets. Finite sets. So this is a proposition, something I'm proposing, right? Let A and B finite sets, and let the size of A equal little a, and the size of B equal little b. Then I'm going to claim the number of functions from A to B is equal to, what is it going to be equal to? Little b to the little a power. Now, why is that? Let us draw a picture, shall we? Let's use a different color for this. How about pink? Pink's a nice color. Let's say this is a finite set, right? So this is a finite set A, right? And here are its elements. And I could draw this because there are finitely many of them. And now let's have B. Here's our set B. Has significantly less elements in it than A does. And let's look at a function, right? Now, the key thing about a function was that an input can only go to one output, right? However, you can always have multiple inputs go to the same output. Think about f of x equals x squared for a second. We know that -2, 4 is in f, and also 2, 4 is in f, right? Because -2 squared is equal to 4, and +2 squared is equal to 4. So multiple inputs can go to the same output, right? So let's have one function that looks like this, right? Have that go there, that go there, that go here. I did not realize how many arrows I was going to be drawing. And this go here, right? And now let's just erase these because I don't want to do anymore. So that's one function, right? And now let's use a different color because we could have another function where say, everything just goes to the same thing in B, right? The key thing is that I pull every element from A, since our domain needs to be that entire set A, and then our image is some subset of B, right? So I want to draw out this picture so now we can have an idea of what we're counting, right? So size of A is going to be equal to little a, right? So we have size of A equals little a, so we have little a many inputs, right? And then the size of capital B is equal to little b, so we have little b many choices for outputs, right? Outputs. So for each element of A, there are B things that it can go to, right? And so from our principles of counting, which we learned so long ago, right? So for our first element of A, how many elements do we have? We have 1, 2, 3, 4, 5. So for our first element, we have B choices. For our second element, we have B choices. For our third, B. For our fourth, B. And for our fifth, B, right? So the total amount of functions that we can define from the finite set A to the finite set B is going to be b to the fifth power. And in this case, 5 is equal to little a, which is equal to the size of A, right? Does that make sense? So for arbitrarily defined finite sets, right? For finite sets of arbitrary sizes b and a, the number of functions from a to b will be equal to little b to the little a power. I hope I was able to emphasize that in that example I just drew out and everything. That was the point of me doing it. I think this is pretty cool. It's a little counting technique that we're first learning. So yeah, that's pretty much all I have to say about functions for now. Next time, what we're going to do is we're going to talk about inverse functions, which again, I'm sure you're familiar with. And we're going to talk about the concept of being onto, one-to-one, and what a bijection is. So if you made it to the end of this video, thank you for watching. I really appreciate it, and I hope you learned something.